Hello, and welcome to this introduction of the Indoor Infection Risk Calculator from KW Engineering. I'm AJ Lowry, one of the developers of this tool. In this video, we will look at how to use this calculator. Before we begin, I would encourage you to read through the Info and Introduction tabs of this document. Keep in mind that modifications to your building's HVAC system should be considered only one part of a comprehensive safety plan, which should also include masking, social distancing, and regular cleaning. This tool is designed to help you understand how different building modifications will impact the risk of spreading COVID-19. There are 4 simple and color-coded steps to follow. In this example, we will be looking at numbers for a typical high school with an occupancy of about 2,000 people. Comments, indicated by red marks, offer additional information on the inputs. Step 1 is to provide general building information. The number of infected individuals is the number of people inside the building that have COVID-19. Several building types are available from this drop-down list. The building square footage and average ceiling height are input here. Step 2 is input baseline building assumptions, including occupancy and time spent in the building per day. The final filter MERV rating is the highest rated filter through which circulated air passes. The percent outside air and total supply airflow rate are input here. A masking policy assumes everyone in the building is wearing a mask. Supplemental filtration includes options such as ultraviolet installations in air handlers or portable air purification devices in rooms. Step 3 is to input the modified building inputs. These are the same parameters as the baseline building, now with modification of COVID-19. For example, alternating schedules and online learning could reduce the number of people in the building and time spent in the building. ASHRAE recommends increasing filters to MERV 13 or the highest possible during the pandemic. ASHRAE also recommends increasing the amount of outside air and total supply airflow where feasible. Finally, a strong masking policy should be enforced, and supplemental air filtration methods may be considered. Step 4 is to review outputs and outcomes. This calculator presents 3 numbers to help you gauge how effective certain HVAC modifications will be. The first is the probability of infection. This is the likelihood that any one healthy individual in the building will become infected with COVID-19 during the specified time period. Next is the anticipated number of infections per day. This estimates the total number of new infections expected to occur in the specified time period. Finally is the effective reproductive number, RT. This represents how many people, on average, one sick individual is expected to infect in the specified time period. Generally, lower values indicate that the spread of the disease will be slow, but values greater than 1 indicate that the disease will spread rapidly. However, infection events will occur outside of the building, and a low RT should not be taken as a guarantee that in the following values for air changes and outdoor ventilation rates are given. Increasing outdoor air ventilation may be difficult to achieve depending on the outdoor air conditions. An additional tool to help you understand the impact of outdoor air in your climate is available at kw-engineering.com under the Mitigate COVID-19 section. Finally, 3 graphs are presented to aid in understanding the output of this tool. In each case, all inputs are held constant from the baseline and modified building conditions, except for the specified variable. The first demonstrates the change in effective reproductive number with respect to the total ventilation rate for both the baseline and modified buildings. In the base case, an RT value of 1 cannot reasonably be achieved and additional action is needed. In the modified case, the risk of infection is reasonably low at the existing ventilation rate. The second graph demonstrates the change in RT with respect to the percent outside air. In the base case, the risk of infection can be reduced by increasing the amount of outside air. However, the RT value does not drop below 1 until the percent outside air is high, which will be difficult to achieve in many climates. In the modified case, increasing the percent outside air slightly reduces the infection risk. The final graph demonstrates the RT value for air filters of different MERV ratings. In the base case, the infection risk is reduced up to a rating of about MERV 13. Above that sees diminishing returns. In the modified case, a similar pattern is seen, but many filters keep the RT value low. It should be noted that local code requirements will have minimum MERV ratings, and that your system will only be compatible with certain ratings. And engineers should be consulted before making modifications to the system. Thank you again for watching. If you have any questions or comments, we would love to hear from you. This tool, as well as our other COVID-19 response materials and our contact information, can be found at kw-engineering.com. Thank you.